There is a massive trap waiting for you in the Cambridge IGCSE Physics 0625 exam. You walk into that hall thinking that just giving the answer your physics teacher taught you, simply stating how a stopwatch works is going to be enough. But let me tell you, what your teacher accepts in class and what the examiner actually rewards on paper are two entirely different things. Today, we're tearing down this measurement myth right away in this explainer. Take a look at this standard student answer for measuring the volume of a liquid. Pour liquid in, look at the number, and write it down. I mean, it sounds pretty logical, right? But the reality, the examiner slaps a flat 0 marks on this. 0. Why? Because Cambridge isn't just testing if you know what a measuring cylinder does. They are testing your scientific rigor. This difference between a casual answer and a rigorous one is exactly how grade boundaries are completely missed and your final grades are risked.
So why does ordinary revision completely fail you here? Well, here are the most painful, common mistakes students make when handling observations. We're talking missing units, rounding numbers way too early in a calculation, mixing up independent and dependent variables, offering super weak practical improvements, and just giving vague explanations. If you're just memorizing textbook definitions without actually learning how to handle data with precision, you are going to fall into literally every single one of these traps.
All right, Section 1, Safety and Apparatus Setup. These are your non-negotiables, the foundational marks you absolutely cannot afford to drop before you've even taken a single measurement. What's totally fascinating here is just how incredibly specific these lab safety requirements are. These aren't just polite suggestions, they are hard exam requirements. You've got to state things like wearing shoes to protect your feet from heavy weights. Dealing with electricity, you better ensure the power is completely turned off when connecting circuits, and only use a low power output initially. Large currents can cause burns, electric shocks, and literally fry sensitive meters. You have to explicitly say you'll switch the power off between readings. Keep water far away from circuits, tie back long hair, wear eye protection around lasers or UV lamps, and handle toxic stuff like mercury with extreme caution. Whatever you do, don't let a mercury thermometer roll off the desk and break. These hyper-specific details are exactly what examiners are hunting for. Okay, so once you're safe, you need the right tools. When measuring mass, length, and time, you've got to explicitly name the correct device, a balance, a rule, a stopwatch. But the real secret is that third column you see, correct usage and range. You've got to ask yourself, does this instrument need to be set to a particular range to avoid blowing it up or damaging it? Are you actually choosing the most suitable measuring device for the specific scale of your investigation? And that brings us to a huge pitfall, the substitute trap. Imagine you're in the lab and an automatic timer just isn't available, so you grab a manual stopwatch instead. But if you just write that in an exam without qualifying it, boom, you lose marks. You have to acknowledge that substituting equipment like this usually results in a much lower accuracy. Why? Because you are introducing human reaction time. The examiner desperately needs to know that you know the compromise you're making. Now listen closely. In just a moment, I'm going to reveal the exact examiner clue that transforms a 0-mark answer into a full-mark answer completely. But to actually recognize that hidden signal, you first need the framework that makes it incredibly obvious. Let's get into Section 2, the 4-step answer framework. This is the high-mark strategy that examiners actually reward when they're grading your practical skills and data handling. Let's walk through this pipeline together. Step 1 is the concept. You need to identify the core physics principle at play, like density or uncertainty. Step 2 is evidence or data. This is where you pull specific, substituted values directly from your measurements. Don't just waffle on about theories, actually use your numbers. Step 3, scientific reasoning. You connect your data to the concept using an equation or a logical method. And finally, Step 4, examiner wording. This is the magic step where you wrap it all up in exam-safe terminology. If you stick to this flow, I promise you your answer becomes bulletproof. Moving on to Section 3, spot the measurement error. Let's actually put this framework to the test with a Cambridge-style interactive challenge. All right, take a really close look at this data table showing volume and density measurements. Can you spot the anomalies? Seriously, look at the headers. Look closely at the numbers. I'll give you a second to figure it out. Did you catch it? First off, there are missing units in the column headers, which is a classic, really painful mistake. Secondly, look at the significant figures. They are completely all over the place down the column. Let me tell you, if you present data like this in your exam, your reliability and accuracy marks are instantly gone. Section 4, correcting a flawed answer. Because spotting the error is only half the battle, right? Now we need to see how to actually fix it using our framework. But before we write the perfect answer, I want you to hear this quote straight from the source's Common Mistakes report. Conclusions not supported by data and weak practical improvements. Ouch! That is the harsh examiner feedback given to students who completely ignored the framework. They make these vague, airy statements instead of hard, data-driven conclusions. We are going to make sure you never get this feedback. So here is the difference in action. First, check out this flawed student answer. The density is around 2 because the volume changed. I mean, it's vague, it's unitless, it's basically useless. Now, compare that to a top-band improved answer. It perfectly applies our 4 steps. It states the core concept of density, it brings in specific evidence from the table with the correct units, it applies scientific reasoning by directly referencing the mass-to-volume ratio, and it uses totally consistent significant figures. It's precise, it's safe, and most importantly, it secures full marks. That brings us to Section 5, your next exam strategy. We've covered a ton of ground, so let's synthesize this whole thing so you are fully prepared to tackle any measurement question. Whenever you finish a question on measuring length, time, volume, or density, you absolutely must run through this mandatory final checklist. Ask yourself, are your units included in every single final answer and table header? Have you used sensible and consistent significant figures? If you had to draw a graph, is the scale correct and does it cover more than half the page? Did you actively consider these specific safety hazards like hot liquids or electrical currents? And finally, just do a reasonableness check. Does your final value actually make sense in the real world? Okay, so here's the deal. You now have the ultimate framework for handling apparatus and data. You know exactly how to avoid those deadly zero-mark traps. But there is a massive unresolved problem. Knowing this framework is completely useless if you execute it using the wrong exam vocabulary. If you misinterpret just one command word, this entire strategy falls apart. Which brings us to the ultimate question. Are you ready to decode that exact examiner language and map out your final 7 days of revision? In our next explainer, we are going to decode the specific vocabulary examiners use so you know exactly what to write and will give you the ultimate 7-day revision map. It is mandatory viewing if you want to secure those top grades. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. See you in the next explainer.